everyone, welcome to this lecture episode from ScaDS.AI, Technical University of Dresden. My name is Sahar Vahdati. I'm a research group lead at ScaDS and happy to present Precision and Recall lecture today, where I'll be talking about why there is a need for integrating knowledge graphs and language models. Before starting, I would like to give some statistics on what's happening now with regards to data, which I believe is driving the progress in AI. All the breakthrough that we are going through is because that much of data that we have currently came together with the readiness of the technologies. So each of the figures presented here, which is from Statista, is basically a zettabyte, which is equal to 1 billion terabyte. If we look at the numbers presented in 2018 and also after some years, what we have now and what is predicted is basically peanuts to compare what is predicted. This much of data is basically telling us that it's a lot out there and yet a lot predicted to be. But I think we are experiencing the breakthrough of AI with large language models because they have high recall. This is thanks to this much of data available. It is implicit knowledge that they are consuming and providing. There is, however, a lot of hallucination, and they are still black box and lacking domain-specific or new knowledge. And this is because that much of data is, of course, great, but it has a lot of things inside it. It is full of errors, fake news, and data that is not structured. Counter technology that we have been dealing for many years already is knowledge graphs, where structured knowledge is present, the accuracy is high, it is interoperable, and it is basically built for domain-specific scenarios. And it is basically handling evolving knowledge. Of course, each of the technologies have their own cons and pros, which we mentioned, but I majorly want to emphasize on the fact of how language models being trained on that much of corpora is bringing high recall to us, and knowledge graph-like technologies are basically bringing more precision because it is structured data. Let's touch on top of the data representation of knowledge graphs, where graphs are data structures comprising vertices connected to edges. Or by edges. And there are also data graphs that we have been dealing for long. However, knowledge graphs is a representation of convergence of knowledge and data as factual statement using a graph model. Why a knowledge graph? Because data is increasingly connected, and it is also the nature of such connected data to be presented or abstracted in graph format to capture all the relationships between the components or entities, as we call it. Graphs are well understood also mathematically, and they are representable with mathematical foundations, and the world itself is structured. We are structured by entities connected by relations. What do I mean by this is basically if we look into the definition of knowledge graph, which is basically a multi-relational directed graph, which is built with nodes or entities and also relation between them. We can look into a triple-like of information representation where a head entity is connected with a tail entity. This is the simplest way of presenting an English sentence, like William lived in Dresden. William is the head entity, or sometimes called subject. Lived in is a relation, and the tail entity or the object entity is basically Dresden. It is a directed graph because Dresden lived in William is not correct, so we have to read it with the correct direction. And of course, this is just the data level definition of knowledge graph. It is much beyond that. It has schemas, ontologies, rules, logic behind it, which we skip for now. And there are also multi-model knowledge graphs, which I will not touch for the sake of the time. But this is maybe a snapshot of a subgraph in a knowledge graph that can give you an idea how it looks like. Another example is that Mobius studied at University of Leipzig. You see the direction from the head or subject entities to object or the tail entities. This is basically a symbolic representation of information, and in triple format, as we discussed before. There are generally two types of knowledge graphs, either followed by semantic web stack, where the resource description framework is used as data model, and the web ontology languages are used for building the ontologies and the schema, and Sparkle is the language for doing the queries over knowledge graph. There are also property graphs, where they are layered property graph data model, and they have also different languages such as Cypher for querying the knowledge graph. And one of the popular ones is actually Neo4j. RDF is the data model used for the first type of the knowledge graph that I mentioned, and also the examples. It is giving us the opportunity to present knowledge in triples: subject, predicate, object, or head, relation, and tail. Data is structured in the form of directed labels, as you have seen. This is another example where I am aligning it with RDF that allows to specify the graph as we defined it so far. And of course, there are complexities there. So there have to be unique identifiers, there have to be objects that can be data values and so on, which would be skipped. Example knowledge graph is DBpedia. It is one of the first knowledge graphs launched over representing data in Wikipedia. The other knowledge graph is Yago, which has a very big ontology and was used by artificial intelligence systems of Watson. And this was originally based on both DBpedia and Freebase. Linked geodata is another domain-specific knowledge graph where, of course, the spatial temporal information is represented in this knowledge graph. Wikidata is another knowledge graph that is built on top of Wikidata. It's basically representing Wikidata knowledge in graph or in knowledge graph. Google has a knowledge graph behind its technology and search engine. And another domain-specific knowledge graph is called Open Research Knowledge Graph, where scholarly data such as publications, survey papers, data, scientific data, and so on is represented in knowledge graph. Following the discussion we started with precision and recall and large language model, why they should be integrated with knowledge graphs, I would like to also remind you on the analogy of System 1 and System 2 for learning and reasoning that is presented by Yoshua Bengio, inspired from the book of Thinking Fast and Slow. System 1 is basically the intuitive and fast mind, which is basically claimed to be the current deep learning. And System 2 is basically the slow one, the logical one, the reasoner one, which is again another pointer to the difference of precision and recall that we have. And I do think that the current large language models that we have, and we are very much fascinated about, are still falling into the System 1 category. They are very intuitive, they're fast, and of course following the current deep learning. However, integration of precision and recall, or so say such large language models and knowledge graphs or structured data, requires an agreement that we say if we agree that deep learning is the foundation and we are going to build on top of that, then there is a question arising how we are going to bring structured knowledge, which is in symbolic representation, to deep learning pipelines and integrate them to have precision and recall together. This requires to have representation of knowledge graph itself in a vector space or numerical way, and one technology to do this is representation learning, where it requires the preservation of all the capabilities or most of the presentation or representation that we have in the symbolic world to be mapped to the vector space. It can be structural patterns, relational patterns, and all of it. For this, to have a representation learning of knowledge graphs, one technology is knowledge graph embedding models, which takes the entities and also relations from the symbolic representation and brings it to the vector representation by projecting head entity to tail entity and performing a transformation specific to the relation between them. Formally, they also follow, as I said, a vector representation of all the entities and vector representation of all the relations, and each of such models follow a score function and also a loss function to confirm the plausibility of triples in the knowledge graph in the symbolic world translated to the vector space. A touch on entity embeddings. They basically a vector of E, which stands for an entity, has a finite number of coordinates. And the index in is called the dimension of the vector, and these coordinates belong to a continuous set, which can, for example, be in real or complex numbers. So there is a discussion coming up here that what coordinate system is used in the design of such models. It can be Euclidean and non-Euclidean, and there has been a long list of models developed, which is basically also affecting the preservation capability of such models, which differ from one knowledge graph to another. That's why there has been a lot of research going on the use of geometry and algebra differently for designing such models. However, there are quite a lot of strong knowledge graph embedding models which are transferring symbolic knowledge and structured knowledge to the space that deep learning methods can be applied. So we are back to what we are seeking here. Basically, there is this breakthrough in AI and deep learning methods that we can call one of the major ones LLMs. There is structured knowledge in knowledge graphs, which is going to basically help with the precision problem of such huge LLMs and foundation models, basically. And there is this technology that is giving us the opportunity to bring structured knowledge in the vector space that is the same space as deep learning methods. Going through the lexical leap and also talking about precision and recall, and looking at the growth in the number of published publicly or closely available large language models, basically we can claim that we have the dream team basically coming together, and that is basically knowledge graphs and LLMs coming together, which is complementary technology to have high recall from one side and also high precision from the other side. This is basically also majorly my research direction. And we have one of the recent research contributions of us presented last year in the ECAI conference, where we look into control natural language semantic parsers for knowledge graphs in question answering systems. And basically we are doing this with the help of large language models. Several other works of mine from recent years, and basically coming to the takeaway from this lecture is basically knowledge graphs are still very important and complementary for foundation models, and we have the technology to bring such models to have their representation learning over knowledge graphs as knowledge graph embedding models. It's still a long way to capture all the knowledge from real world to knowledge graphs and from knowledge graphs to other spaces. So my conclusion is that however all achieved is staying in system 1 level, and we need to build the connection and integration between large language models and knowledge graphs to have high precision and recall together. Thank you very much for listening to this lecture.